Okay, so for question number 2, we wanted to find the work from 1 to 2 right there. And since PV to the 1.4 was a constant, I used the equation that you got for that, and I got work is negative 269.3 kilojoules, the PV constant equation. And then for work, and then, and then for work 3, 4, delta U, and then is equal to Q, and since it's an adiabatic, I think that's how you pronounce it, type, I was able to get Q is equal to 0. And then you can do U4 minus U3 is equal to negative work of 3, 4, given by the energy conservation equation. And so I just found U4 and U3, subtract them together, get equal negative work, and I got 686.37 kilograms of work. And then I found the volume also using the PV constant, so I could fill out the PV table. I found the volume using that formula, 100 kilopascals, and then we'll move on to the second page. In the second page, we need to find Q of 2, 3, and then Q of 4, 1. So I just used the energy conservation equation and then plugged in the works that I got, or since work was 0, since volume was constant, you didn't need to do that, so just found U3 and U2, and I was able to get 2, 3, and then also U1 and U4, and since volume was constant, 0, I was able to get Q, and then for the efficiency of it, I did the net work over the Q in, and since we only had one Q in, which was 2 to 3, I just put that, 804, and then turned out to be 51.07% for efficiency. And then for power cycle, I added up all the works, and since it was greater than 0, it was a power cycle and not a refrigeration cycle. Okay, on to problem number 3. So since we know it's an assumption is that it's an ideal gas, and we have the mass, I was able to find the volume at V1 and V2, and then also at V3. So here's my equations for that, and then there's V1, V2, V3. And then the same energy conservation equation, delta U equals Q12 minus work. 1,122.82, is equal to Q12 minus W12. And so we have, since it's expansion work, we're able to do the P of V2 minus V1 for finding out that. Oh, sorry, the camera's getting a little hard to hold up. Okay. Then I was able to find the work from 1, 2 using that equation. And then I also did the U2 minus U1. Since we were given the U's for state 2 and state 3 is equal to Q12 minus the work, which we just found in that equation right there, to find the heat generated by 1, 2, which is 920 kilojoules. And then to find the total heat transfer between to find the heat of Q23, we have net energy is equal to Q23 minus work 23. And then to find the work for this one, and since it's a temperature constant in an ideal gas, I use the PV ln V2 over V3, and this is a V3 over V2. To find work 101, and then since there was no delta U, no net energy change given by, if you looked, and I got the net energies from the table A22, because this is an ideal gas and it's air, and it's in a closed system, so you could just use that to find the net energy. And that's how I found the net energy for U1, U2, U3, and PV, and then did this equation to find the work, and since there's no net energy change, since they both were the same, I used it to find 2Q3, and then I added them all up, and I got 1930. Okay, pass the page. Okay, then we're on to problem number 4, and here I drew a little schematic of the turbine. And in part 1 it was 10 megapascals, 520 degrees Celsius, and then Q is going out with work going out. And then so the assumption is kinetic energy, potential energy is 0. and we did the PV diagrams, which are down here, and since state 1, it was superheated, and then in state 2, it stated that it was X equal to 0.92 mixture, so I knew it had to be in this region and then superheated up there. I looked at the table to find those out. See, right here is at 100 bar, it's 311 degrees Celsius, but we had 520, so it's superheated right there. Then it's state 2, 1 bar, temperature supposed to be 48.81 degrees Celsius, but it was much higher than that. And we had mass flow rate, so I did the energy conservation equation. And since we do have heat loss and we do have work being done, and then we just had to find H1 and H2. And so since it was superheated, I was able to find H1 there. And since it was a mixture, you had to plug in the HF, the X, and the HG, and the HF to find out what the H was. And so I got the H to be that. And then I just plugged everything in and found the Q to be negative 398, which works because negative means it is leaving the system. Okay, and then here's for problem number 5. This was a system of equations, and here's the trickier problem. So we had a turbine, condenser, and heat exchanger thingy-madoober. So we have all the states, state 7, so state 1, 2, 3, 4, 5, 6, 7. The assumption, it's an ideal gas, no Q loss from the compressor or of the heat exchanger, and work is... Okay, never mind. So the first CV that I took was the turbine because I wanted to find the work going from the turbine to the compressor because that's how I thought it works since there's a big like green bar between there, and why did you give us those two? So I used that and I found the work to be 1.98 kilowatts going from there to there. And then I took CV2 as the compressor using state 1 and state 2 as an inlet and outlet, and I should say for CV1, the turbine, I used state 6 for the inlet, state 7 for the outlet. And then here's my work for CV2. So I plugged in the work that we got, and since kinetic energy and potential energy are assumed to 0, you can just cancel those out, same for up there. And then you already have the mass flow rate of the steam that's in the condenser already. It was 0.018. So we're down right up there. Right there. And then just H1 minus H2. So we had to look at the table for water to see what the H1s and H2s and whatnot and what they were at. And you're able to find them because you're given the temperature and the pressure for both of them. So I was able to find that. Or actually, you're finding for H2. This is what I did. I found for H2. So we had H1, but we didn't have the temperature for state 2. So I wanted to find for H2. So I found for H2, got 215. And then CV3, which was the heat exchanger, we needed to find that H2 so we could figure out what the mass flow rate of the water would be. Seeing as we didn't have H2, so that's what I did. And then the mass flow rate of the water would be the mass flow rate of the the water that was cooler temperature through the heat exchanger would be 0.18 that, because you do the energy equation and work and power 0, and it got to be 0.058 kilograms per second. Probably should have wrote that in. That's gonna get points off, but whatever. And there is my other thing. I'm sorry for completing it late. I totally forgot about it since I had another test today that I had to study for right after, and I took it during it was actually, my test was during that time period of 12/17, so I'm sorry I wasn't able to send it earlier.